be Chapter 8, problem number 47 in the textbook. This is a good problem, especially for dealing with RC and RL circuits, because it has two power sources, and you have to determine an R Thevenin in order to figure out what your resistance is going to be for your RC circuit. So I'm going to start pretty much at the beginning. This is going to be a much more in-depth video, and it's going to go over some of the very basic concepts for those who need it. So feel free to skip ahead if you need to. And the next video, the one that will be on the quiz question, will be a little bit more focused on just doing the math. But to start, we're going to talk about a couple topics. The first one being this 12 right here. Attached to that 12, of course, is that U of t, which, for those of you who are not super familiar with it, is the step function, which means that at 0, you're going to change from 0 to 1. This step function is multiplied by 12, so this will instead become a 12, and this will be 12 volts once you get to time t is greater than 0. So that also leads me into the whole purpose of doing t is equal to 0 minus and t is equal to 0 plus. The reason you're doing this is because you're trying to find when your circumstances change. How does your circuit react? So that includes but isn't limited to how your capacitor reacts, and then you want to see what happens to the rest of your circuit. You're essentially doing circuit analysis, but you're trying to find your initial conditions is what you're doing. Because when your circuit changes, then all of a sudden your capacitor, it's no longer like DC. When it's been charging and the circuit's been relaxed for the last who knows how long, there hasn't been any changes to it, your capacitor and the rest of the circuit is going to almost act like a DC source. Or not source, but it's going to act like it's been in DC. Whereas we know that capacitors and inductors are more active during AC when there's changes. So this is going to be measuring those changes and then finding an equation for your either voltage of your capacitor for all time of t is greater than 0, or it's going to be your inductor current for all times greater than 0. However, this one doesn't have an inductor, so we're going to focus on the inductor, but that's why we're doing t of 0 minus and 0 plus. You got to remember, this is still 0. That's why the values stay the same, right? The VC of 0 minus is equal to VC of 0 plus, right? They stay the same because you're still at 0. Similarly, in this function, at 0 minus, you're at 0, but then at 0 plus, you're at 1. Technically, no time has passed. All this happens at 1. That's why it's a discontinuous function. But you're measuring the changes, because at 0 plus, okay, now you're up here and you're going to start moving stuff here. And then at 0 minus, you're still down here. So, but for capacitors, the value is going to be the same. And same thing with the inductors. Your IL of 0 minus is equal to IL of 0 plus. Now, it doesn't mean their derivatives are the same, right? Like your IC of 0 minus is not the same thing as your IC of 0 plus. So don't think like that, because remember, the IC is C dVC over dt. You can have a change in your voltage happening, and that can be different between 0 minus and 0 plus. But your actual voltage will be the same between the two, and similarly, your inductor current will be the same between the two. So, all right, now we're going to get into the actual problem itself, but wanted to make sure we established those few things before we got started. So let's begin by doing a circuit for when time t is less than 0. And you don't know how long the circuit has been like this, but the goal is to figure out what does your circuit look like before you make a change. And so in this case, that change is going to be this U of t. So at time t is less than 0, in this branch, keep in mind this and this means that all of this is parallel. This whole branch is parallel, so I'm just going to draw it slightly differently. You have your 2 kilo ohm resistor. You have your 5 milliamp source, and this 5 milliamp source is going to stay the same the whole time, right? It's not going to change because it doesn't have any sort of time value attached to it. This one has the step function attached to it. This one does not. So this 5 milliamps is going to be on the whole time. Then you have your 2 kilo ohm resistor here, 2 kilo ohms, and that, remember, is going to lead to your VC, which in this circumstance is going to be an open circuit because it's T. You don't know how long T has been this circuit has been in this relaxed state. So it's been on for so long that it's going to be DC, and at DC, your voltage of your capacitor is just going to act. Your capacitor is going to act like an open circuit, which can still have a voltage. So, but there's a couple things to note here. Because this is an open circuit, your IC is 0. And this is again for less than 0. So for IC of 0 minus, you're going to get 0. Okay? Now we need to analyze this circuit. So the key to this circuit is this right here is your voltage of your capacitor, which means your capacitor is seeing all the rest of this circuit. That sounds pretty similar to something, right? That's similar to the Thevenin and the Norton equivalents. So we're going to find the Thevenin and Norton for this circuit. Actually, we're probably just going to find the Norton here because you really want, when you're deriving your differential equation and when you're finding initial values and such, you're really looking for a lot of the currents. You're looking to find this VC, but when you're trying to do your differential equation, you're going to be using the currents, which is something else we're going to get to when you're doing the differential equations. Your VC, well, if you want dVC over dt, which is what your differential equation is going to be built by, you want your I of C, right, divided by C. That's the same thing we wrote earlier, right? So when you're trying to find your VC, you're going to be using a lot of currents. When you're trying to find your IL, you're going to be wanting to do the opposite, where you want your DIL, LDIL over dt. And what is this value? It's V of L. So you're going to be wanting a lot of voltages because that's what your derivative of your IL is. However, this again is not an inductor problem, so we're going to go back to trying to find this VC and the rest of the values needed here. So for t is less than 0, once again, we're going to try to find this Thevenin equivalent for right now. Well, all these branches are parallel to each other. So this resistor is parallel to this resistor, which means we can just combine them. So this Thevenin is actually going to be pretty easy to figure out. You can do a lot of circuit analysis, or the other way to do this is you can do VOC over R Thevenin is equal to I short circuit, right? So we could short circuit this. We could also just find an R Thevenin by shutting this power source off, right? This is not dependent. So to find the R Thevenin, we could just shut this power source off and then, combine the resistors accordingly. Any of those really works. So let's do it that way, where we turn off this power supply, and then we say, all right, so our Thevenin is going to be equal to 2 kilo ohms parallel with 2 kilo ohms, which a lot of people like to use that little quick formula. I like to just 1 over 2k plus 1 over 2k to the negative 1. I just like to do it because it works for 3, 4, 5 resistors. But the way that a lot of people do it is totally acceptable as well. In this circumstance, this value is going to come out to 1. To the negative 1 is still 1. I'm sorry. This is actually going to come out to 0.001, which inverse is 1,000. So 1,000 ohms, which I'm going to label as 1 kilo ohm because it's just going to make this circuit a lot easier. So let's put this back now, because it didn't technically go away. We were just measuring our Thevenin equivalent, or I'm sorry, our Norton equivalent technically. So let's redraw this circuit now, now that we have a Norton equivalent resistance. So we know we have our 5 milliamp source. we know that we have 1 kilo ohm in parallel. And then we know we have over here our VC. Okay, that's wonderful. Now, you can do, again, there's a million ways that you can solve this circuit specifically, but this VC is parallel to this branch, right? Which is also parallel to this branch. So if we say, you know, you have one loop going around here, because this is an open current, right? IC is equal to 0. So if you know you have one loop, all of this 5 milliamps is going into here. 5 milliamps times 1 kilo ohm is 5 volts. So that's going to be our VC of 0 minus. Okay? And that's just because you know that this VC is parallel to this whole branch, which means they're going to have the same voltage, right? And again, you could theoretically do a couple things to figure that out, but ultimately, I mean, you could do like nodal analysis right here too if you really wanted to. But the gist is that our VC of 0 minus is going to be 5 volts. And then we said earlier, VC of 0 minus is equal to VC of 0 plus. So that means that our VC of 0 plus is equal to 5 volts. Okay, so now moving on, now that we have the value that we needed for time t is less than 0, let's move on and redraw this circuit in an applicable way for time t is greater than 0. T is 0 plus. And so this is where we're going to draw the circuit at first, and then I'm going to write out these steps. So we're going to draw the t is equal to 0 plus circuit. And we're going to draw this so that we can derive our ODE, our ordinary differential equation. We'll call it a function. And then, so that's step 1. Then step 2 is we're going to do find solution for VC 0 input, and then we're going to find solution for VC 0 state. And I think everybody has a basic grasp of doing this, but we're going to kind of derive it this way. And so when we derive this right here, that circuit that we draw is not necessarily what's going to be applied to both of these, right? Because 0 input means that we're turning our sources off. 0 state means that we have nothing in our storage device, in our storage components, your capacitors and your inductors and such. So they're not exactly the same thing, and that's why I'm separating these three. But let's take it one step at a time. So let's go with, at first, this, let's draw the circuit at time t is greater than 0. So if we go back up to here, we have this 12U of t, right? This is now on. This is now going to be 12 volts. We still have this, which is still parallel to the rest of these. We're just going to draw these two in series with each other on one branch. This is still on. This is still the same. And this is now going to become a voltage source. At least at t equals 0 plus, it's going to act like a voltage source that has 5 volts. That's not a permanent thing. Obviously, that's why we're finding the value for, or the equation for VC of t, because it's going to change over time. But at this point in time, at 0 plus, it's going to act like a voltage source. And similarly, an inductor is going to act like a current source. I guess technically I should draw that down if I'm going plus minus that way. It's going to act like a current source, again, only at t equals 0 plus. And it's only going to have that VC 0 minus, which is equal to VC 0 plus, value at 0 plus. Then the circuit's going to change, but that's why we're doing what we're doing, so that we can figure out what the total equation is. And that's why you have all the e to the negative t's, or, negative t over tau, through all these circuits, because that's how it's changing over time. It's a natural exponent. So we're going to redraw this circuit now, and we know that we had that resistor, and then we know that we have this power source, this voltage source, So that's going to be 12 volts. This is still 2 kilo ohms. This current source did not go away. 5 milliamps. And then this over here is still a 2 kilo ohm resistor. That's a really bad ohm. And then down here we have what I was talking about, which is the voltage source. Let me make this cleaner. Plus minus VC, right? So this is what our function, this is what our T is greater than 0, T is equal to 0 plus circuit is going to look like. So once again, we are kind of looking at, okay, we're going to need to find a few values, and we can still kind of cut this off and figure out what our equivalents are for this circuit. However, we're going to use this at first to derive, well, actually, yeah, let's do that, because let's condense this thing into a Norton equivalent first, because we want to derive this equation, and the most ideal way to do that would be to set up the Norton equivalent first, and then we can derive based on those values. So for a Norton equivalent, you have this this voltage source and this resistor in series with each other can be converted so that we can make a another current source, right? And in theory, you can also, once again, do a whole bunch of nodal analysis or mesh analysis. I don't usually like to get rid of components and condense them into smaller things, but it works in this case because, once again, your VC, there's no dependent sources, and your VC of T it sees the whole circuit. So in this circumstance, we can change everything to, well, actually, let's make this the current source. This is going to be our new 2 kilo ohms. This is over here. This is the 5, and another 2 kilo ohms here. And all of that is seeing our voltage over here. Okay, so once again, we're going to have, this is 5 milliamps, this is 2 kilo ohms, this is 2 kilo ohms, and this is, and so now we need to do the source transformation, which 12 volts divided by 2 kilo ohms means it's 0.006 amps, which is 6 milliamps, right? So this current source is going to become 6 milliamps. Okay? And then once again, now we can combine this circuit. So our final T is equal to 0 plus circuit is going to end up being this right here. You can combine these because they're parallel. You can combine these in parallel the same way we did up top, so it's the same value. So this is going to become 1 kilo ohm. This is going to become 11 milliamps. And then this is going to be your capacitor. But the bigger reason for doing this, while this is going to help us later because this is going to make we've done a lot of the math that's going to make our lives a little bit easier later on. The important part to remember here is that what we're trying to derive is our differential equation. So the easiest way to do this is we're going to say KCL right here at this node. We can call this node VA if we really want to. But the KCL involved is going to be, you have IS, the IS being your source current, you have your IR, and you have your IC, right? So this KCL has the IS going in, which means it's going to be negative, plus your IR going down that branch, plus your IC. And that is equal to 0. Perfect. Because we've only got a first order differential equation, we only have one storage charging component. That means that this is pretty much the only equation we're going to need in order to derive this formula. Let's keep in mind that your VA is actually equal to VC, right? because this VA is parallel to this branch. So this VA is the same value, which means we can move this IS over to the other side, which is what we want, right? Because you're in a driven circuit. I should probably write this down. In a driven circuit, your source is equal to your solution. Your source is your solution, which means, like, you know, if you have, you know, dVC over dt plus VC, this is your solution on this side, right? So that solution is going to end up being your IS, which is exactly what we want. So moving on, we're going to now derive this equation. So we just said that IR is equal to, well, we just said that VA, right? VA divided by whatever your R is going to be your IR, right? I mean, that's just deriving from the current. I'm sorry, that's deriving the current from the voltages and the resistance value. So we can rewrite this as IR plus IC. Oops, that was a really bad I. IC is equal to IS. And now we can bring this down and say VC over R plus, and what is your IC again? It's C dVC over dt, right? And that is equal to IS. Okay, this looks pretty good. The only difference is this is our lowest value, right? And we do not want that value to have a coefficient. So we're going to divide this whole thing by C, both sides and everything. So our final differential equation for this circuit is going to be dVC of t over dt plus 1 over RC VC of t, which is equal to IS over C. Okay, so that was this is a big step, right? This is a huge part of what we want in order to solve this problem. And again, that's derived from the entire circuit at t is equal to 0 plus. Okay, so that was step 1. Step 2, right? Because this was the derive our ODE function. All right, so step 2, we're going to now find the solution for the VC of 0 input. So 0 input, let's bring this down. Let's copy this, bring this down to here. So 0 input, the key here is that we're not going to have any inputs. I mean, it sounds obvious, but let's redraw our Thevenin equivalent. And so this time we're going to have a current source of 0 amps, still with this resistor in parallel. And then this VC is still exactly the same, VC of t. Okay, so what changed here? This is still 1 kilo ohm because this is from our Thevenin, or I'm sorry, our Norton equivalent. So what changed here? Well, this is now 0 amps. That's equivalent. The easiest way to think of this is, because this is 0 amps now, you can almost think of it like an open circuit, right? You can have a voltage across this, but you're not going to have any current going through it. And that's really the key with the 0 inputs. The 0 inputs doesn't mean to do the traditional, like, oh, if it's a voltage, it becomes open, and if it's a current, is straight through. No. When you do the 0 state and 0 input, those values become 0. So for a current source, no current goes through it because it's 0 amps, which is actually like an open circuit, more so than it is like a short circuit, right? And actually, it's not at all like a short circuit, because a short circuit will have no voltage, but it could still have current. So I'm hoping that wasn't super confusing. The basic gist is, remember that when you turn off your sources for 0 input, they become 0 times, or 0 of whatever you're trying to, or whatever their source type is. So 0 amps for a current source. Now, you still have a VC, right? And you still have 1 kilo ohm over here. So your VC of 0 plus is still 5 volts. That's still the same thing from before. You still have your charge stored. The only thing that changed was your inputs. Your storage component, which is your capacitor, did not get affected by changing the equation like this. But what does this mean? Well, remember we said that this was our IS, right? Well, there is no IS anymore. This is 0. Nothing's going to go down that way. It's a 0 current, right? So your IS is equal to 0. 0 amps. Well, plug this back in here, and we can rewrite this equation, dVc of t over dt plus 1 over RC Vc of t is equal to 0. All right, now let's solve this differential equation. So let's move on down here. Let's just plug a couple values in. dVc of t over dt plus 1 over 1 kilo ohm times 20 microfarads was the value of our capacitor. And just to double check, yep, 20 microfarads. So this value, and this is times Vc of t, is equal to 0. This is going to now become dVc of t over dt plus 50 Vc of t is equal to 0. And that's just plugging in the value. We know that it's going to end up being 50. And so now our goal is to do the solution portion of this. So you only have one order, which means this is just going to be an S. The S squared is when you have the d squared Vc over dt squared. So this is just going to be one S since it's only one order. Plus 50 is equal to 0. Okay, your S is equal to negative 50. Cool. So now we can plug this all into our general guess equation. So that means that our Vc of t guess, and actually before I go too far into this, this is all 0 input. It's not going to kill anybody if the 0 input's not in there, but just to help keep track of everything, this is all for the 0 input attempt. This is the general, right? And then these are all regarding the 0 input portion of our thing. So Vc 0 input of t is equal to our guess, which is AE to the negative 50t. Okay. Well, this part, it's important to remember that your 0 input and your 0 state are separated, right? Those are going to be two different solutions that you're going to plug in. So at this point, we can plug in our initial conditions for the 0 input. This is the entire 0 input equation. We can now plug in our initial conditions, and we should be able to find our coefficient and figure out what this A is. So remember that Vc 0 input of 0 plus is equal to 5 volts, which is equal to AE to the negative 50t. And technically I could write this right here as a 0, right? Because we're measuring at 0. So this whole thing goes to 1. E to the 0 is 1, which means that 5 volts is equal to our A. Nice and easy. So that means we can rewrite this as Vc 0 input of t is equal to 5 e to the negative 50t. Okay, that was a huge part, and that was the entire 0 input solution portion. So now we're going to redraw our circuit once again, this time dealing with the 0 state, right? So let's draw t is equal to 0 plus, and this is going to be 0 state, which if we go back and look at our instructions, you derive your ODE, you find your Vc of 0 input. Now let's do the 0 state. So the 0 state circuit is going to look like this. So 0 state means we have our sources back. Actually, this is correct, drawing this again, but it's all, we can start from here. We can start from here, because this is not necessarily wrong, but we have already helped ourselves, which is nice. So this time, we're going to draw our voltage source, which is our Vc, and this value is 0, right? That's because this is the 0 state. That means that our charged components, our charge components, essentially our time varying components, are 0. So this is 0. This is still these were 2 kilo ohm before. This is 5 milliamps. This is 12 volts, and this is 2 kilo ohms. Now, what is really nice about this is that we've already helped ourselves before. This whole portion right here, all this, is the same thing as what we had earlier. So we're going to go ahead and do the Norton equivalent just for the sake of ease. So we have 11 milliamps. We have, that's a really bad resistor, a 1 kilo ohm resistor. All of that is attached to 0 volts. Okay, now remember what I said before. The 0 amps current source almost acted like an open circuit, right? Because you had no current going through it. Well, this is going to be the opposite. 0 volts means that you have no voltage. There are no voltage drops going down that branch. But it doesn't mean that you don't have any current. And as a matter of fact, you have all of the current going this way, because if we consider this like a short circuit, let's do this in red. If we consider, let me undo that and just do this in red. If we consider this a short circuit, then that means you're going to bypass this resistor entirely. Why would the current go down a branch that has a resistor when it could just go down another branch for free? So this is 0 volts. All of this is 0 volts. And that means that this has 0 volts. And all of that is just because it's a short-circuited circuit now, right? So that means that our VC of 0 plus 0 state is equal to 0. All right. But our IC, and I don't think we're actually going to have to use the IC in this circuit because it's a first order, so we don't have a plus B type of thing going on. But in theory, our IC is equal to your 11 milliamps, right? All of the 11 milliamps are going to be going down the branch that has the capacitor, based on the short circuit analogy. But I don't think we're actually going to use this. I should put 0 state, 0 plus is equal to 11 milliamps. I don't think we're actually going to be using this for this equation. But just to keep that in mind if you see it, a similar or something like this in another problem. Okay, so now the other thing we're going to deal with is we're going to go back to this formula, 0 state over dt plus VC 0 state of t, I should have put the t, is equal to IS over C. This should have the 1 over RC. Okay, so this equation is more like a regular ODE that you would solve the mathematical way, which means we're going to have to break this down because you have this value here and this is all still a differential equation. So now we're going to have to take this function and split it off into 2 branches, the homogeneous and the particular. So we're going to have to now do both portions. So let's focus first on the homogeneous, which means we're going to have the same 0 state homogeneous over dt plus 1 over RC VC 0 state homogeneous. I guess I should be putting my t's, is equal to is equal to 0. Because the homogeneous equation means that we don't have any anything on this side. And mind you, this is different than before, right? This is because mathematically you solve it by making this side 0 and then finding the particular solution, which includes our IS over C, separately, right? That's very, very different from setting this equal to 0 because of your source current, right? Because up here, for 0 input, what we discovered with our 0 input was that your IS was 0 once you turn this to a 0 amp source. So these are two different ways to do it. I understand how there could be some confusion, but one is derived from the circuit, and this one is done mathematically. And that's important, mathematically. And that's important because this is 1/2 of a solution. You are not going to plug in your initial conditions until you have VC0 state is equal to VC0 state homogeneous plus VC0 state particular. You cannot plug in your initial conditions until you have that entire function. Okay? So this is a mathematical 0, not necessarily because of the circuit. But now moving on, we're going to go into this function. It's going to be exactly the same as we had before. You have an S plus 50 equals 0. So that means that our S is going to be equal to negative 50, which means that the general solution, once again, to this equation is going to be VC0 state homogeneous is equal to AE to the negative 50t. Okay? It's a really bad 50. Okay. So that is your VC0 state homogeneous. Now your particular is going to be solved in a bit of a different method. So I want to make sure that I do this correctly. Okay. So our VC0 state particular, your guess is that it's going to be a K, right? And this K is derived because of the fact that we don't have any sort of time varying, we don't have it, I don't want to say time varying. But actually, you can technically say that because after you get to 0 plus, right, you have no, let's go back to the original circuit. You don't have anything here that's varying with time, right? After 0 plus, this is 12 volts. After 0 plus, that's 5 milliamps. So those are just constants. You're not changing with time at any point, which means you're just going to have some sort of constant is what your final value is going to be particular for the particular solution. Now, Dr. Moreno likes us to also keep in mind that technically we are also adding the derivative dk over dt, but the derivative of a constant is 0, so you're not going to be doing anything with it. It's essentially just k. Now, the other thing to keep in mind is when you solve like this, you need to find what your guess is, which would be this, and then you also need to find as many orders as you have according to your guess. So your dVC0 state particular would be the dk over dt, which we established a second ago, is 0. If you had a second order 0 state over dt squared, then you would also want to do this. However, in this equation, we only have one order, so we're not worried about this part right here. But just keep that in mind. If you're doing a second order, you need to do this derivative again. You need to do the second derivative. So this is 0. Now let's plug this whole thing back into our differential equation. So you've got dVC0 state, particular over dt plus 1 over RC, VC0 state particular. Technically, I should have been putting these t's is equal to k, right? Now let's substitute. Let's substitute with purple. So this we established was k, right? I'm sorry, this is not k. This is we established that this one was 0. This is not k. This is what your actual value is, which is 11 milliamps. This is your this is your IS. IS over C actually, so divided by 20 microfarads. So let me go ahead and redo this part right here then. So this is your IS over C. This is coming from your initial differential equation. So I'm sorry if that was confusing. This, we just rewrote the differential equation that we had initially. And then we took our guess for our VC of zero state particular and the derivative of it. We're going to plug those in. And then here, this is the original function because we're doing the particular, right? So this one's not equal to 0 anymore. And this is now, we're just plugging this in, 11 milliamps divided by 20 microfarads. Okay. So now we have pretty much everything we need. Let's reset this up. So this is going to be 0 plus 1 over RC K is equal to, and then 11 over 20 microfarads is 550. 550. And this, so let's rewrite this. This is 0 anyway. This is 50. K is equal to 550. So K is equal to 11. I guess I should write this in the regular color. So our particular solution is that right there. So now we're going to use this function right here. We're going to put all of it back together. So we had a VC zero state of T is equal to VC, zero state homogeneous, VC zero state particular, which means VC zero state total is equal to AE negative 50T plus 11. Right? Now, our job here is to plug in what we need to in order to get our VC of zero state, which is equal to 0, right? Well, I'm sorry, of 0 plus. We're using our initial conditions. This is an initial condition, is what I'm doing right now. So plugging this in, we're going to find what this A is. So VC of zero state of 0 plus. Well, our capacitor voltage is 0, right? We established this here. Our capacitor voltage is 0 at 0 plus. That's why it's 0 state, because the state of the charged component is 0, which means that that's equal to our AE to the negative 50, negative 50 times 0 plus 11. This is going to go to 1, which means that A plus 11 is equal to 0, which means our A is equal to negative 11. Okay, so now we have a VC 0 input, VC 0 state is equal to your total VC of T. Okay, so you have both of these values at this point. When you combine this back together, VC 0 state of T, T is equal to this right here. We know that our area is negative 11, so negative 11 e to the negative 50t plus 11. Okay? So let's plug these in. So your VC of t is equal to, what was it at the beginning, 5? This right here. So 5 e to the negative 50t plus, well, we can just put negative 11 e to the negative 50t plus 11. Okay? Which is going to come out to VC of t is equal to 11 minus 6e to the negative 50t. Okay? So this should be the final solution to our problem, which it is, and this is correct. And actually, because we, so what's the one thing I'm missing here? Because of the fact that this is all solved for t equals 0 plus, that means that this whole function right here is going to be multiplied by u of t, because it got changed at our time t equals 0. So this function is valid after 0. But this right here is our total and final answer. Thank you.